Welcome to The Explainer. Today, we're plugging into the crazy high-tech revolution that's happening right now to keep our lights on. It's this amazing story of how our power grid is literally learning to predict the future, all to stop the next big crisis before it even starts. So what actually keeps the lights on? It's one of those things we totally take for granted until, bam, the power's out. Well, the answer is this unbelievably complex, continent-spanning machine we call the power grid. And right now, that machine is under more pressure than it has ever been. And I mean stretched to its absolute breaking point. Think about it. For decades, this critical infrastructure has been getting older and older, while our hunger for electricity just keeps growing. Then you throw in the chaos of more and more extreme weather, and yeah, you've got a system that is constantly on the edge. Okay, so here's our game plan. First, we'll look at why our grid is so stressed out. Then, we'll explore this huge shift from just reacting to problems to actually thinking about risk. We'll get into the cool multi-sensor tech they're using, how that data leads to smarter decisions, and wrap it all up with how AI is basically giving the grid a super brain. Let's get into it. All right, first up, our grid under pressure. Before we can even talk about the fixes, we've got to get a handle on just how big the problem is. And trust me, it's not just one thing. It's more like a perfect storm of challenges all hitting at once. Okay, so what are we dealing with here? Well, on one side, you've got the physical stuff, right? The infrastructure is old, we're all demanding way more energy, and of course, these crazy weather events are becoming the new normal. But that's only half the story. There's this other massive problem, and it's all about data. For years, the information from inspections was just a mess. It was fragmented, stuck in different silos, and worst of all, you could have two experts look at the same thing and come to totally different conclusions. So all this pressure, it's forced a huge, fundamental shift in thinking. Utilities just can't afford to play whack-a-mole with problems anymore. They have to get ahead of them. And that means a completely new way of looking at their most important assets. And this new way of thinking is built around a concept called asset management. Now, this isn't just about fixing stuff when it breaks. Oh no, it's way more like a high-stakes balancing act. You're constantly juggling cost, risk, and performance to get the best possible outcome. And this whole idea has really grown up over time. I mean, it started out super basic, right? Step one was just fix it when it breaks. Total firefighting mode. Then it got a little smarter. Let's replace stuff on a set schedule. Okay, better. Then, even smarter. Let's replace things when they start looking worn out. But the real game changer, the big leap, is this fourth step, risk-based management. This is where the question changes completely. It's not just, is this thing broken? It's, what's the damage going to be if this thing breaks? That changes everything. Okay, so that leads to a big question. How in the world do you get the kind of data you need to make these smart, risk-based calls? Well, the answer is you basically give your inspectors technological superpowers. You let them see things that are totally invisible to the naked eye. Just look at the difference here. The old way was literally just relying on human eyes. An inspector looking for a crack or some rust. And hey, that's useful, but it's totally subjective. The new way, it's a whole different ballgame. We're talking about a multi-sensor view that sees heat, electricity, physical wear, and gives you hard, objective data. It's not about opinion anymore, it's about facts. So what's in this new toolkit? Think of it like a complete physical for the power grid. You've got your standard RGB camera. That's like the doctor's visual checkup, looking for obvious stuff like cracks. Then you've got infrared, or IR. That's the thermometer, spotting dangerous fevers from things like loose connections. And then there's the really cool one, ultraviolet, or UV. This is like the MRI. It sees these invisible electrical arcs. It's called corona discharge, which is often the very first clue that something big is about to go wrong. And this quote just nails it, right? Each sensor sees a different piece of the puzzle. None of them gives you the whole story alone. You might have a hotspot that shows up on infrared, but looks totally fine on the UV sensor. Or the other way around. The magic happens when you bring all that data together. You fuse it, and suddenly you see the whole picture. And you can make a way more accurate diagnosis of what's really going on. Okay, so you've got all this amazing high-tech data pouring in. What now? Because, let's be honest, raw data is pretty much useless noise. The real magic, the part that actually matters, is turning all that noise into clear instructions. Something that tells a crew, go fix this right now. And this takes us right back to one of the biggest headaches, human subjectivity. Seriously, without a standard system, you could give the exact same thermal image to two different highly skilled inspectors. One might look at it and say,
let's just keep an eye on it. The other might look at it and yell, shut it down now. That kind of inconsistency, that's a massive, massive risk you just can't afford to take.
So what's the solution? You have to create a common language. Everyone needs to be reading from the same playbook. And that's where standardized frameworks, like the guides from EPRI, that's the Electric Power Research Institute, come in. They basically create a rule book. It means a specific kind of heat signature or a certain level of UV activity gets graded the exact same way every single time, no matter who is looking at it.
And this little matrix is where it all comes together beautifully. You look at two things. First, what's the condition of the component? Is it in good shape or poor shape? But then you ask a second, absolutely crucial question. What are the consequences if this thing fails? I mean, a failing part that powers a single farmhouse is one thing, but a failing part that powers a hospital, that's a whole other level of urgency. This matrix combines those two questions and spits out a single, simple priority score.
And that score isn't just a number for a report. It directly translates into action. A high severity score? That means all hands on deck, this needs immediate attention. Medium severity? Okay, that gets scheduled for maintenance pretty soon. Low severity? We'll log it and keep an eye on it. It just makes the whole process logical, efficient, and, this is important, defensible. But wait, there's one more amazing layer to add here. What happens when you take all this data and plot it on a map, using a Geographic Information System, or GIS? Well, you start to see the bigger picture. You can spot patterns you would never have seen otherwise. Like, hey, why are all these components failing near that one factory? Or, whoa, this specific part seems to be corroding way faster along the coast. Suddenly, you're not just fixing individual problems, you're seeing system-wide risks. And that brings us to the final and maybe most exciting piece of the puzzle. Let's talk about how this whole thing gets supercharged by AI and how it's pushing grid reliability into the future. So what does AI actually do here? Well, think of it as the ultimate analyst, one that never gets tired and is incredibly accurate. It can chew through thousands upon thousands of images, automatically flagging potential problems. But even more impressive, it can look at the data from all three sensors, the visual, the infrared, and the UV, all at the same time, and find these tiny little connections that a human brain might just miss. And that means fewer false alarms and less wasted time. And then it gets even cooler with something called geospatial AI, or GeoAI. This is where AI goes beyond just finding what is wrong and starts to figure out why it's wrong. It does this by mashing up the inspection data with location and environmental data. Things like, is this in a coastal area with lots of salt spray? Is it near an industrial polluter? It starts to connect the dots and find the real root causes of why things are failing. And this really shows you the evolution of where this is all going. In the past, our data was just descriptive. It could only tell us what already happened. Right now, we're in the diagnostic phase. We're using AI to understand why it happened. But the holy grail, the future, is predictive. Using all this amazing data to know with confidence what's going to happen before it actually does. So, you see, the goal has completely changed. It's not about finding faults anymore. It's about predicting the future. We're moving from being, historians of past blackouts to being architects of a future where they just don't happen. The big question has shifted from how do we keep the lights on today to the much more powerful question, how do we make sure they never go off tomorrow?